Start recording. Wow, what happened to my water? Alright, I don't care. We will run it until I feel thirsty. But I'm gonna be honest with you guys. I'm gonna talk a lot. So, Eson sent me some papers. 2 of them I already read. He sent me previously. Therefore, we may look. But more importantly, last time we had a talk, we had some thoughts, sharing of thoughts. Especially, he was sharing more on how ranking works. How is like this fucking 1 over log 1 plus r thing. And I had some epiphanies since last week. I want to share with you. Alright, we have, this is one paper, counterfactual learning to rank via knowledge distillation. Then we have lambda loss, which is a new paper. And then we have search ranking policy via marketplace expected value. This also, this formula matters here, that we have the formula for DCG. What is wrong with it? Alright, perfect. But before reading these papers, well, 2 of them I already read. Before reading lambda loss, let me, this formula and this formula, this is counterfactual learning to rank via knowledge distillation. This was the teacher-student model, right? We talked about it last time. These formulas are getting more complex. But we have teacher model and we have a student model. Let's go, let me talk first and then we will go over the rest. Therefore, I'm gonna share my let me look at these notes. Okay, my notes are here actually. So the whole idea of ranking comes from my experience last week. Last week, Andrew and I were in the line of a bar and the sidewalk was kind of like slanted. No, it was slanted. I was here. This is not me. I was here and this was Andrew. Andrew has long hair, so this is Andrew. And there was other people here. I draw their eyes. And I was talking to them. Yeah. I was talking to them and I said, hey, I actually asked Andrew, so there were other people we were talking to, but okay, it doesn't matter. Well, we asked their opinion at the end. That's why it's important. Other people. This is the other people. Alright. So I told Andrew, are you taller than me? And then he said no. And I asked the other person, I said, this is me, right? And this is Andrew. So, and the other person also mentioned that I am taller. Amir is taller than Andrew. That was the story. 5 minutes later, not 5 minutes, 10 seconds. After 10 seconds, Andrew says, wait. Andrew says, this fucking sidewalk is slanted. Alright? So what we did was like, okay, let's switch side and see who is taller, right? This was Andrew. Came here. You. Okay, his long hair now is this way. And this is me. And then it was kind of Andrew is taller. So we were like, okay, we are pretty the same height. That was the epiphany, right? And then we were talking to this red person, and I thought, I'm studying ranking. That was the epiphany moment for me. So the whole ranking system, what is the whole ranking system? The whole ranking system, we have an idea that this ranking comes with a organic, natural boost. If it is the ranking, and this is I want to say attention, right? Probability of sale, but let's say attention. So we know, we kind of, based on a lot of experiences, we kind of got that ranking, this R, gives you an organic boost. For now, let's assume this curve is, we talked about fairness a lot, but for now, the curve is fixed. Alright, so these positions, these ranks have value by themselves. Alright, and it is probably, what is it, log 1 over log 1 plus r. So when rank is 1, it is 1 log 2. Well, this is for what they consider in DCGs. Then log over 3, you get more attention. Then also we have another metric which is not ranking. This is ranking here. I want to say close to attention. They're the same kind of thing, but it is relatability, relatable, or quality of a product. And we have like M products, and this is 1 to M. They have a quality, like this one is this quality, this one is this quality, this one is this quality, this one is this quality. Alright? This one is this quality. Everybody has a quality. And if we keep this order, because what does ranking do for us is that it kind of, sometimes it, based on your model, sometimes we can say it's adds, or we can, in the DCG example, we can say it like multiplies. So let's assume that this just, the ranking just gives you a boost and pushes the thing up. So we have this, comes from ranking, then rank 1 is here, it's here, now rank 2 is here, rank 3 is especially here, so because number item 3 was so tall, it's already here. But look at the difference here. This difference was this much here. Here now they are much closer to each other. Right? And then rank M is here, but now because of the ranking it's this, and the difference between rank 1 and rank M is this, which is much bigger than this difference. So what is ranking if the fairness, if we assume that this push doesn't change? Well, we know that in short time it doesn't change, right? Forget fairness for a while and let's assume this attention curve stays like this. So that's ranking. Perfect. And what we want to rank, for example, we want to rank one thing that DCG is missing actually is that DCG is just one metric and we want to know what is DCG maximizing. I feel DCG is maximizing relatability. What it says is that, okay, I have two decreasing function and I mean, let's assume we want to say if it is like a summation, it doesn't matter how we order them, right? It doesn't matter because if you want to sum the effect of each, if it is summation, the order doesn't matter because summation, like if you are like summation, you can change the order of summation and it doesn't matter. So we have like pi, the score of pi, and then we have the ranking. F is ranking 1 over log 1 plus r f of I, and the other one is pi of I, sorry, relatability of item I, r of I. So if we say it is final effect, g of I is 1 over log of 1 plus pi of I and plus relatability of I, item I, that is like, then some g over I is independent of I. So that is not good. But if we assume some metric that like DCG that says it is Ri, Fi, then this is depends on pi, which we know it depends on pi. So something like Ri over log 1 plus pi I. It is like DCG. And which pi we should choose to maximize, right? Let me see if I can find the formula here. Exactly here. So R is here rank, and R hat estimate of relevance. So that's this multiplication. So ranking the DCG part is fixed. 1 over Fi is log, it is the attention boost because of ranking. That's item I's gets. Attention boost from ranking. And Ri is the relevance. Now what the whole ranking and consumer behavior story starts is that, like the person, the red person, that couldn't see me and Andrew on a level surface. He had to decide based on this boosted slanted surface which one of us is taller, right? So what people observe here is two items. We have I and J. What they observe is Ri over log 1 plus pi I and Rj over log 1 plus pi j. Well, that sounds very easy because they know I, they know j, and then it's easy. You can compare Ri and Rj. And if you want to say, for example, let's assume a simple metric. If pi I, we wanna maybe one objective. If pi I is less than pi j, meaning I has a better rank on the top of the list, then we expect this comes from minimizing DCG, right? Ri be greater than Rj, right? Let's assume all of the R's are positive and you want to maximize, you want to choose a pi that maximizes Ri log 1 plus pi I, right? Over I, argmax. What pi maximizes this term? And without loss of generality, we can assume relatability of item 1 is greater than relatability of item 2, greater than Rm, greater than 0, right? So where should I put item 1? Item 1 is different than its position. Now we want to decide where to put our position, right? You have two functions, sigma Ri, Fi, right? Maximizing over F, to maximize, we need to be greedy and sort F. We want to have, this is actually what I had in my previous one too. F1 greater than F2 greater than Fm. So pi needs to be arc sort of Ri. That's it. If for DCG, which I guess it is for click-through rate. Somebody may say we want to maximize revenue. Should we maximize for DCG? No. Somebody may want to say then revenue leads to another ranking, right? It just depends who has the most relevance, right? Let's assume we have this simple case. We have two stairs and there is whoever makes it above this threshold, which I'm gonna make it blue, will sell, right? And we have two people, one is this tall and the other guy is this tall. If I put them this way, both of them sell. But if I put them this way, only the tall guy sells. So for me as the platform, right? Maybe in the in the way that the tall guy is in the lower stair, the tall guy still is selling, but not as much as the first one. But now, for me as a platform, the second one, the total sale will increase. Let me see if it is true. This is a additional case. Maybe in an additional case it doesn't even work. So this guy is X, and this guy is Y, and this Y, and this guy is H, and let's assume everybody sells proportional to their height after threshold. So Y minus H is blue leads to Y minus H plus, what is this difference? It's also Z. Z plus X, and black leads to Y plus Z. That's it. Black leads to Y plus Z, even for a summation case, right? While blue causes to Y minus H plus Z plus X, which is Y plus Z plus X minus H. Therefore, if X is greater than H, well, why? X is less than H. We know that X is less than H. So if X is less than H, this will be actually less than Y plus Z, which will be less than black. So this mechanism here says actually it is better for the platform to give the taller guy the taller step. But notice, I set it the objective function in this way. Another objective function may lead to another thing. I said, okay, the height after the threshold matters. And that's it. Okay, that's really good. Another thing that we mentioned, how to compare, which is about local minimum, is that how to compare to okay. So the thing is that, all right. The thing is that we as a platform, we are the red person. We don't know as a platform. Perfect. Okay, that was the question that Ehsan was asking. We as the platform can only observe Ri over if you can observe this, to be honest, then we can observe Ri easily, right? That's not very difficult. If we can observe the boosted relevance, then we can observe relevance itself. Because we know what the rank is. So the only assumption that can make it not true anymore is that we don't know the weight of the ranking. This assumption should go away, log 1 plus pi I should go away. Okay, this is one thing, alright. This is one thing. Okay, now maybe the ranking problem in e-commerce is different from ranking problem in the height measurement that I said is that in height measurement, the person was looking at both of us and saying which one is taller, right? Here in ranking, we just say what data e-commerce has is that one option got clicked. Once one option is clicked, because the user or consumer only buys one of those products, clicked, do we know that they looked at the other option or no? Like, let's assume item 2 was clicked, right? Maybe the person just saw option 2, right? Number 2, item 2 and item 1 and said, okay, R2 is greater than R1 and chose R2. Right? You put it into a consideration and said this is better. Sometimes, and then they didn't even look at item 3 and 4. Then we cannot say, okay, R3, over log 1 plus 3 is definitely less than R4, R2 log 1 plus 2. It may not be the case because we don't know. The clicking on something doesn't mean that other things are seen or not. Do we know the impression or not? And now this one brings us to, so one thing I want to mention is what objective function leads to DCG. 2 is data of e-commerce data of e-commerce says once something is clicked, okay, we can say it is relevant, and the noise that okay, it was a wrong click, something, okay, ignore it. But if something is not clicked, it doesn't mean that it was compared with the clicked one and said, okay, the clicked one is better. No, it doesn't mean, because you are showing thousands. There are objects in the like other pages. If you like a list of 10,000 and people look at the 5 pages, 5 items on the top, you cannot compare it with the other ones at the bottom of the list and say that they are better. It says, okay, data of e-commerce cannot say if something was clicked because it was not clicked, it was bad or not seen, right? And 3, I want to talk about local minimum. And then I changed the order D and D prime and So okay, if you look at the what we are ranking means this permutation of objects, right? And we wanna find the permutation that matches the best relevance. For example, let's assume we know the relevance. Assuming we know the relevance, we want to find the permutation that matches the relevance. And you know that in the space of permutation over m objects, you can make it from, which is functions which are 1 to 1 and onto from 1 to m to 1 to m, right? I don't remember what do we call them, but functions that just swap the position of two objects are the building blocks of permutation space, and like in the group algebra or something, kind of algebra thing, group thing. So they are building blocks, and from each permutation to another permutation, you can move from each permutation to another permutation, just switch every time switching two objects. Alright? This can be done. And so the local minimum thing was that we want to assume you have a pi, right? You have a pi star that minimizes sigma Ri, and let's assume now that Ri's are not decreasing. Ri f of pi I minus Ri f of pi star I. So this pi is a local minimum. This is greater than, less than or equal 0, right? Because pi star minimizes the cost. If it is the cost, so this is greater than or equal 0. It says we don't need to search. If we have one pi, it's kind of definition of gradient. If we have one pi, let's just compare it with the pi's that are next to it. Because the space of all permutation, the size is n factorial. But the space of permutations that are next to it is just 2 out of n, which is like n minus 1 over 2. So it gives, we can find the local minimum this way, but is the local minimum the global minimum? That's the question. Is local minimum the global minimum? I don't think so. By the way, this LR, I don't know where it comes from. For LR 1 log 1 plus R, this is not pi I. This is not probability density. So these are the questions we had. I think this should be in this paper. No, okay, again, the same paper. It's at the end of the paper. Right? This is swapping. Okay. So I wanna know. What I wanna know is first knowing DCG and LR. And then we can the switching thing, let's put it at the end. Local minimum, let's put it at the end. And I want to know where DCG comes from. We want to also talk about cognitive load. So where is the DCG coming from? Then I wanna study. I wanna study DCG. First is DCG. I talked about my epiphany, which is good. Data of e-commerce. Oh, okay. The other thing is that if something is clicked or not clicked, did the impression happen or not? And then, okay, let's go over ChatGPT. First of all, let's look at the essence paper. Maybe we can find it. Here is about the DCGs. Okay, these equations also matter. We talked about them, and it matters. It actually is their model. In this model, they have some assumption on user behavior. Maximum C pi is clicking. DQ. So for a query Q, we come up with a bunch of results, which is called D of Q. And pi of DQ is how to sort this DQ items in the DQ. C of pi of DQ is the probability or expected probability of clicking once we give demand list. What is the probability that the list get a click and the user does not exit, given that user went through this journey S before Q? The expected number of desirable engagements across all the slots on the page. Slots on. What does that mean? I thought it was clicking. It is clicking. Suitably parameterized ranking policy by hypothesizing an explanatory click model based on hypothetical or causal constructs that govern user browsing and engagement behavior on search result pages. Well, we need to come up with a new one. We can build effective likelihood models from which we can estimate the parameters of the ranking policy via maximum likelihood estimation using logged observational data. That's great. We instantiate this process with the simple widely adopted click models in information retrieval, which is 1 over log, assuming a vanilla sequential browsing model. That's a good assumption. Along with the standard position dependent examination model, we can write the expected number of desirable engagements as, so we have n items. Tell me the item at rank R, probability of the item at rank R being clicked, right? This is the summary. That's easy. How many clicks we get? Like one item, first of all, one item gets clicked. What is in general probability of? That C is the sum of all the items that got clicked. And the expectation of 1 if it clicked, if not clicked is the probability of them being clicked. And what is DQ? So this is actually very good. I like the first line. This is complete general model. I love it. So item on rank R is clicked, probability of given the history of the search so far plus and all the items prior to rank R have been observed in a way. Then here is a critical assumption that they are saying it doesn't depend on the prior. That's a big assumption, right? It doesn't depend on the items prior to item R at the rank R, which is item pi minus 1R. It just depends on the position of the rank. And then equals probability of you being clicked by yourself depends on probability of you being observed, and then probability of you being relatable. If you are clicked, you are clicked if you are observed, and you are being relatable. So observed is 1, right? And then this one comes from where? This one, do we have an equation for it here already? I think we have this formula in the other one. This one. Probability of being clicked equals probability of you being observed, and we assume that observation and relatability are independent, which is a very good assumption. Why not? If you are relatable independent of your position. And if you are observed, usually it says that you're observed because you went on the screen. It doesn't depend on you being relatable or not. I say that's a really good assumption. I don't want to change it. And so that's it. But why probability of being observed doesn't depend on the search history. It just depends on the query and doesn't depend on the rank number. Sounds it should depend. Wow. Whaley. It should be S plus, thank you. But probability of being observed, you're saying it doesn't depend on R. Why not? An item being observed depends on R. If anything, the probability of relatability doesn't depend on R. Actually, I say this one should, equation 9 should change. Alright, I better go back to my main notes, by the way. Probability of O given R. And then probability of O pi minus 1 of R equals 1 because it doesn't depend on Q. 1. Relatability doesn't depend. Okay, may depend. Because we are choosing pi. For one, if we fix pi, it doesn't depend. But if we choose pi from sequential rising assignment with click event on the item rank at position R and DQR representing the slotted items prior to the item ranked in position R. The second line follows from the assumption, assuming that the user interaction event on a given slot is independent of the placed items in the previous slots. Well, that's a big assumption. We talked about it. The third line follows from the standard examination-based click model that posits that a click event can be expressed as the intersection of a query-specific examination event examination and a representation independent contextual relevance event presentation independent relevance. Okay, it is independent of relevance. So why do you keep that? Okay, R should be independent, but O should be dependent. That's what I said. Alright. And the last line follows from assuming a query independent global rank discount function on the examination probability. Okay, this also assumes that independent of the query, which we know that for different classes, for example, once you wanna buy a Rolex watch, you spend more time, unless you're super rich, alright? But based on the observed data, for example, more expensive items, people spend more time than you want to buy a paper towel. You just choose the first one. So this one, they are saying this global rank discount function. This global rank discount function comes from DCG, which is 1 over log 1 plus R. We have our question, where is this coming from? Something we observed or something? It's not even probability. Probability. So it should, if it wants to be like that, it needs to be cut somewhere. From assuming a discount function on the examination probabilities, the examination probability is also known as propensity. Well, examination probability. Well, you cannot be like that. Probability, it's not a probability. Right? Dude, 1 over n is not summable. You're saying 1 over log of n is summable? No. Our context is specific. The examination also known as our context is and can be estimated via explicit online interventions or from observational data. By considering a simple univariate model fit on the estimated propensities as a function of rank, one can build data-driven rank discount functions to estimate users' examination effort. However, the standard approach is to adopt vanilla log-based context-oblivious rank discount as generic estimates of examination probability. Well, this is wrong because this is not a probability density. Given an empirical estimate R hat of base contextual relevance, on one can derive the standard discount decimal. Alright, that's it. I'm not gonna pursue this further. Let's answer our question. By the way, I have to simplify my note and go back to my thesis. Alright, I wrote this stuff. I'm gonna clean them. We have them in our overleaf. Exactly. Cognitive load. These are all written down. Retailers. So I feel somebody will win a Nobel Prize studying recommender systems. Okay, this is we talked about. We talked about. That's it. So we talked about all of them. The things we want to mention now are one. One is okay, I told this to Exxon, so I'm gonna remove this. Actually, I wanna keep it. And editing new notes, I did it. Let's add this stuff. And then we can talk about that. These are cognitive mode model and user behavior, two things that are similar. That's this part. One. User behavior model. We have user behavior model, we have EQ7, improve. EQ7, where is it? Search ranking policy. Learning. Two, cognitive load model. Three, also this can relate to Nagin's paper. Three is, I forgot. I have to jump between the two. Actually, that's the stupid type of note. Adding note to Google Doc. LLM. That was Monzer's suggestion. Ranking is like writing a sentence. What comes next? For meeting before September 22. I don't know, we can't do that. I forgot my meeting with Monzer today. That was fucked up. Five. Multi-touch and momentum. That's another subject. I don't want to add it here, even if the engineers. Okay. This is another thing I mentioned. Maybe it is lambda loss that talks about. Five. in a given ranking, and perfect. Let's go. I want to chat with ChatGPT now. Yeah. What is DCG in ranking? Dude, a lot of oil. I add too much oil. 2 to the relevance, not relevance. Well, okay, that would be a new relevance. Well, it says it measures how well the ranking of items like web pages or products aligns with their relevance to the user query or interest. The thing is that how well up to what metric? The key idea is to assign higher importance to relevant items that appear earlier in the rank. But relevance, what up to what? Relevance up to maximizing your revenue, relevance up to helping consumers find the products right away. How DCG works. DCG calculates the cumulative gain of items in a list. Applying a discount factor that reduces the gain of items as their position in the list increases. Applying a discount factor for that reduces the gain of items. Yeah, oh, it is log 1. Yeah, that's the same thing. As their position in the list increases, yes. So if your relevance is high, we wanna 2 to the relevance I minus 1 is the same as relevance, right? If your relevance high, we wanna keep you at the top of the list. We wanna keep your I small. Pi. The formula for DCG at a particular rank position pi is this. Relevance of I square discount factor. It's not the probability. Why use DCG? Position sensitivity recognizes that users are more likely to enter near the top of the list. Relevance grading accommodates varying degrees of item relevance, not just the binary relevant, non-relevant classification. Okay. Comparative evaluation facilitates the comparison. To enable fair comparisons across different queries or datasets, across queries. DCG is often by ideal, which represents the maximum possible DCG for a perfectly ranked list. Okay, that's a smart. DCG of this pi compared to the perfect one. But again, perfect one, here they assume that maximizes the possible DCG. But it says like, what is the metric behind DCG is still a question. Okay, that's just bullshit. Application of DCG. Search engines evaluating how effectively searches recommender systems, assessing the relevance of machine learning models, training and testing ranking algorithms in tasks like document retrieval and person. Key takeaways. DCG measures the effectiveness of a rank system by considering both the relevance and their position. This counting ensures that relevant items appearing later in this leads to the overall gain normalization. So where is the discount factor 1 over log 2 1 plus I come from? Where does? Is designed to model decreasing importance or attention that users give to items as they appear further down the ranked list. Here is where it comes from and why it's used. If we know this, the organic boost of the list, that really helps us find the relevance. But if we don't know that too, that's difficult. The discount factor 1 over log 2I plus 1 is in the discounted is designed to model the decrease. Okay, rationale behind the discount factor. Rationale or rational? Rationale. All right. User attention decreases with rank. Empirical observation. Perfect. Studies in information retrieval and user behavior have consistently shown that users pay more attention to items at the top of a search result page or recommendation list. The likelihood of a user examining an item decreases as the item's rank increases. Cognitive load. Wow, I love that. Users have limited time and cognitive resources. They are more likely to find that what they are looking for among the top rank items and may not scroll through the list. Modeling the diminishing importance. Nonlinear modeling diminishing importance. Nonlinear decrease. The decrease in user attention isn't linear. It's more rapid at the top and tapers off as you move down the list. A logarithmic function captures this behavior more accurately than a linear function. Logarithmic discounting. The logarithm function grows slowly, which means that the discount factor decreases rapidly at first and then more slowly for higher rank. This aligns with how user engagement typically drops off. Discount factor definition. So it's just based on observational data and it captures well. But the thing is that how did they find it? Because they cannot remove Ri. Y log 2 I plus 1 offset by 1, adding 1 to the rank I. Discount factor for the first position is this one. This means there are rank discounted consistency cross position. This offset and smooth decrease in the discount. Okay, base of the I like that, but you may also want to find it in a, you may go deeper study and come up with a better thing. Right, what is Negin paper? Negin paper doesn't have log to open. Plus 1. So let's go over this. Attention drops. DCG. What objective function ECG discount factor one over log 2 1 plus I is not probability Negin's model is probabilistic and doesn't have log 2 assumption. All right, and well, other bases doesn't just the scaling, interpretability using made calculations, information theory, connection to information, relevance in the numerator allows for a greater score, emphasizing the importance of, well, you can choose a lot of things. Cumulative game. Smaller. You want to maximize DCG, right? You want to always maximize DCG. So DCG is not a cost. Gain. DCG is a gain. Sorry. DCG. Early satisfaction. penalizing lower ranks, alternative discount, reciprocal rank, has realistical, hybrid model, some metric you just based on empirical user behavior, data to better models, context, again, context man, why logarithm is preferred, empirical fit, it aligns with them, practical implications, designing ranking algorithm. Actually, I want to save them. Can I save? I don't want to search them all the time. Can I? Oh, share chat. I need to create link. Okay, practical input. Understanding the discount factor helps in designing algorithms that prioritize placing the most relevant. So DCG is something we want to increase. Relevance ordering by emphasizing early user satisfaction. Engagement metrics. Origin of discount. Reflect user behavior. Alright, that's it, just from practical. Answer. Well, okay, they say observational data, but how did you drive that from the observed data? Because as we know, the observational data says is the mix of relevance and these terms, the boost. So it's interesting to know that. And we assume users do not. Let's have a big assumption that users do not tend to game the system. Consumers, which is very, who wants to change the ranking of Amazon? No one. Most of them, right? Intentionally, actually. Like flooding happens, but it's not intentional. All right. What is the lambda loss? Is there a probabilistic model? So, by the way, I want to look at Nagin's paper. These are just talk. Why do you have problem opening them? Okay. That's actually really good. This is Nagin. Okay, I have to go kickboxing. Stop it now, we will come back and check them. Thank you.